Okay, hello everyone. This is kind of intended to be a compound video. Um, it is, I believe I don't have installed the current version of STAR-CCM Plus, so it'll be installing that, starting it up, opening a simulation, and going through a basic simulation for a cylinder. Now, mind you, there's a couple of things that I don't have any intention of diving into a huge amount of detail on because these are better covered in um, other videos that have been posted in the playlist on Canvas. But it will go through the entire process from basically top to bottom. So, hold on a second. Let me pull up something really fast. If we look at the playlist that I believe I linked to everyone, it has a number of videos. It talks about separately in different videos geometry, which is one you're probably going to want to look at. Selecting physics, regions, creating regions, a walkthrough of a basic 2D conical diverging nozzle. How do you mesh things? How do you create boundary conditions? How do you create reports, monitors, plots, and scenes? How do you know if it's done or not? How do you know if it's stable or not? Let me see here. What else? Did we do a cylinder in here? We did not. We will, however, do a cylinder today. So do look at some of these videos. This video is not a substitute for looking at some of these. It is supplementary, shall we say. Let's see here. So, installing, we have the client that has been downloaded. We attempt to run it, we need to extract all these files. Just extracting to the desktop ought to be fine. Nothing fancy needs to be done. We will give that a second to extract all the files, and then proceed with the installation. Wait, where did my, there we go. Perfect. Yeah, so these are extracted, so now we'll run this here. And we'll start the install process. As usual, there's some terms and conditions that need to be accepted. We're going to switch over to a custom install instead of an express because there are a couple settings we need to change. You could either select or deselect this. I'm going to leave it selected. Doesn't really matter. Generally, this is installed to a local path on the local computer. So the things we definitely need are what is currently selected. We do not need the virtual reality or any of the CAD clients, but I'm going to install the CAD clients anyways because I have the space, and why not install everything? The important thing that you definitely need to do is do a network install with SimCenter STAR-CCM Plus Power on Demand. Power on Demand is the licensing that we will be using. So it will configure it and then should let you start to install. It will absolutely say that this 1999 at flex.cdadapco.com does not serve a valid license. That's fine. That is expected. Go ahead and hit next. You can modify these as needed. Usually, you do need to allow the firewall to let it through. You will need to have internet access to run the software. Share the install directory will just let other users on the same computer use the installation. And then you can create a desktop shortcut or not. So we'll let that install. Hopefully, I am not doing silly things and did not try and install this in a location that has very little space. It's got some space. It doesn't have a colossal amount, but that'll do. Clearly, I need to clear some stuff off of that hard drive. Okay, so it's installed it. Now, we have a couple of shortcuts on the desktop. You'll notice there's actually 3 of them, in my case. Clearly, you can ignore the virtual reality one. This one that has the CVI shortcut is a viewer. This will let you look at things, but not actually do any simulation work. And the one we want is SimCenter STAR-CCM Plus 23.6.0001. This is the version of the software that has been installed. This will run simulations. And hopefully, it will look something like this. So, what we can do here is... Hold on a second. We will start a new simulation. Actually, just... yeah, that one's outdated. Bear with me a second here, because I don't want to entirely broadcast a power on demand key to the entire world. I'm going to do this on another monitor briefly, and then bring it back. Actually, tell you what. For first off, the settings here, you want to generally, unless you're doing something pretty special, do parallel and local host with the number of cores you have minus 1 or 2, depending on how many cores you have. I'm blanking on how many cores this computer has, so let me find out. At least on Windows, you can find this out by looking at the properties and finding the processor, and then you can just look up the processor. And in this case, this has 16 cores. This is a little bit weird because some of the cores are faster than others, but I'm going to tell it to use 14 cores. That can go away. So 14 cores. This is 2 less than the computer has available. And we will need to use power on demand licensing. The server will need to be this 1999 at flex.cdadapco.com. That's fine. We will need to change the POD key to the one that I provided for the class separately. So this is where I put this in separately and bring it back in a moment here. So I am just copying in that key. And double checking that everything looks okay. Yep. Okay. There we go. Okay, so I copied over the key, I hit OK, and it's trying to start a new simulation. We'll give it a second here. And hopefully it'll pop up with a little file tree on the left-hand side. There we go. So it did manage to properly check out the license from the Power On Demand server, the 1999 at flex.cdadapco.com. So we have a little folder tree here. Well, the very first thing I'm going to do here is say save as and save it somewhere. So if you just try and let it use its default, it will probably yell at you because it tries to save in the installation directory by default, at least under Windows. While the installation directory is under program files. And most things, unless you give them admin rights, do not have admin privileges, so they can't save in program files. So you need to save it somewhere else. I'm saving this just on the desktop, and I'm just calling it cylinder. Nothing fancy. So, the workflow. I talked about this a little bit before, but we're going to want to look at a cylinder at several different Reynolds numbers. I believe the restrictions I provided were between 10 to the 4th and 10 to the 6th Reynolds number. That is between 10,000 and 1 million. That must be a minimum of a factor of 2 apart. And then to test 3 different Reynolds numbers, the velocity must be less than Mach 0.25. And I forget what other restriction. I think I said it had to be a gas. But other than that, I don't think I provided any limitations. But first of all, we're going to want to look at several things: pressures, velocities around the cylinder, the drag on the cylinder, things like that. But we need to create our cylinder first. I do recommend looking at that geometry video that I showed earlier. This will give you some more insight into the tools. However, we will go through creating the basic geometry here. This is simple, shouldn't take too long. So the first thing is, let's create our cylinder. This cylinder should exist with its axis on the z-axis. We're going to go ahead and place it at the origin, that's fine. And a meter is probably on the large side. We'll make it 0.1 meters radius. And we did just create it. You see on the top left here under parts, there's the cylinder. But we can't see it. This makes it hard to tell what we're doing. Like, you can still figure out what has happened, but it's harder. So under scenes down here, we're going to right click and say new geometry. And it will create a new geometry scene. That is a 3-dimensional or spatial visualization of the geometry. Hey, we have a cylinder. You can see it's actually 1 meter long and has a 0.1 meter radius. So now what we need to do here is create a block to represent the air around the cylinder. So we're going to go a good value. 5 is probably a little bit excessive. We'll go 3 meters upstream and 12 meters downstream of this cylinder. Remember, this is 0.2 meters across. So we're going 15 diameters upstream, and we're going, I don't even, what is that? It's like 50-ish downstream, give or take. In any case, and we probably want to be, let's go -3, +3. So this is a 6 meter tall box, 15 meters long, 1 meters wide. And one thing that's actually pretty important here is that one side of the box is at the z equals 0. This will be a 2-dimensional simulation, and one of the restrictions of STAR-CCM Plus is that 2-dimensional simulations must lie on the XY plane. that is parallel, or they exist on a plane that is parallel to xy and is at z equals 0. So coincident with the origin. This z equals 0 ensures that. We're going to hit create. Notice it does not close the tool. It did create it, but it didn't close the tool. So we have to hit close ourselves. If you hit create twice, it'd create 2 blocks. So I'm going to call this air. Now, the thing here is, when it creates a block, it's just created one surface. Like, we have no way of distinguishing the front from the top, from the bottom, from the side, from the back, etc. So we just have one surface for both of these. That's less than ideal. So we're going to hit create, or select both of these and say, in this case, split by angle. And we're just going to let it split by 89 degrees. So if faces have a 90 degree or a right angle turn on them, they will be separated. Well, this is a box, so it has 6 faces, and hey look, we have 6 faces. We probably want to name them so we know what's what. So we're going to rename this, the back, as an outlet. We're going to name the top, obviously. The front is going to be inlet. The bottom is going to be bottom. This is going to be, well, I'm not actually sure which this one is. This looks like it's the z equals 1. I'm going to call it out of plane. That is, it is parallel to our simulation plane, but it's not the one we're simulating. And call this other one plane. And the cylinder, we're going to split by angle. It's going to create 3 surfaces as well. I'm just going to call these somewhat generic because it shouldn't matter too much. I'm going to call that cylinder. Okay. So now we have a block, a solid rectangular prism, and a cylinder. And I'm going to make this slightly easier to look at by doing this. Hold on. View normal. There we go. Now, the thing here is, this block currently is solid. It does not have a hole cut out of it. If we want to cut out a hole, we need to tell it to take the cylinder and remove it from the block. This will be an operation. This is what is known as a Boolean operation, specifically a Boolean subtract. We are taking one thing and subtracting it from, or we're taking a couple of things and subtracting the rest of them from one of them. We're going to select both the air and our cylinder. Let me open that up again to see this. And we are going to say, hey, the thing we are going to cut things away from is the air. So this will take everything in the inputs, and then it will cut all of them away from the one you specify. So in this case, since we only have 2, it will look at the air and the cylinder, and it will subtract the cylinder from the air. We can right-click and hit execute, and it will do it. And we have, hey, a part that's called a subtract here. And if we look at this, we highlight this, you can see that it's the exact shape of that block, except it's got a hole in the middle. This is exactly what we want. And if we look at if we expand this file tree a little bit, we can see that it still has a bunch of labeled surfaces. It has an inlet, it has an outlet, it has an outer plane, a plane, a top, and a bottom. It has all the named things. It also has a cylinder. So it has all of the surfaces that we need. So now what we're going to do here is we are going to say, we're going to take this subtract and make it a region. So geometry isn't actually the thing that gets simulated. It's just a shape. Things that get simulated are known as regions. So we're going to say assign parts to region. We're going to create a region for all parts is fine for the moment. And a boundary for each part surface. This is important. Definitely do not leave it as default because otherwise it will go badly. You can leave this as default. This doesn't matter. This is a more advanced topic for now. Okay. We have a region. So we have our subtract, and we now have basically said, hey, this subtract is something we do want to simulate. And we have a whole bunch of boundaries. This is exactly what we want. Now, we only want to simulate this in 2 dimensions, so we need to actually do something special here. Under operations, we need to go to mesh and say badge for 2D meshing. This is a way of saying, hey, I do want you to simulate this thing, the subtract, but I only want to simulate this in 2 dimensions. Oh, and actually, I should have done that first. So I'm going to delete this region and then recreate this subtract region. There we go. Okay. We have our region again. We have our subtract and a couple of things you want to look at to make sure this knows that it's doing this in 2 dimensions. For starters, is it when you did this God, what's the word I'm looking for? The mesh operation, the badge for 2D meshing, it didn't throw any errors in your face. It says it did it. Look down here. But it didn't throw any errors in our face. It didn't say it had a problem. So that's good. It succeeded. We can also see that the subtract has a little red dot. I don't think I can really zoom in on that, but subtract has a little red dot. And also, these symbols changed. One of these is a solid red, like, sheet of paper. The rest are sheets of paper with a little outline, and there's one with a gray or, like, bluish interior. So these are telling us that the ones with the outline are the perimeter of our 2-dimensional simulation. And the red one is the entirety, like the actual plane that we're simulating. The geometric plane. So there's a couple, you can do this in a couple different orders from this point forward. But what I'm going to do right now is define the physics that are going to matter here. So I'm going to select these models and say, we're going to just tell it what matters. Well, this is a 2-dimensional simulation, so space is going to be 2-dimensional. This is going to be a steady simulation, so we're going to select steady. It is going to involve a gas, so we're going to select gas. This starts to get a little bit more technical at this. Coupled flow is generally for high energy flows that have a lot of energetic exchange going on between like temperature or something else. We're not going to have that here, so we're going to select segregated flow. Now, we could probably get away with constant density. I'm going to select ideal gas because it's more general purpose. It's more general case and doesn't overly complicate things for the most part. We're going to select segregated fluid temperature, so it's allowed to track the temperature of the fluid in order for the purposes of calculating the ideal gas law. Now, we could tell it how much viscosity matters. Does viscosity not matter at all? Is the flow inviscid? Is the flow going to be laminar? Is the flow going to be turbulent? Well, if you know anything about flow around cylinders, it's going to be turbulent. And we get some choices in turbulence models that we could select here. Some of these are better than others in different cases. The complexities are different. They will influence the amount of time it takes to simulate this in different ways. They will give more or less accurate results in different scenarios, depending on what you're looking at. So, for our case, we're going to look at K omega. This is a generally okay case, or generally a good selection. when you need to look at something that you know is going to have flow separation, and it matters where the flow separation occurs. And it's also not going to be painfully obvious where it occurs. I believe I talk about that more in the physics selection video. You can go look at that later. We shouldn't need anything else, anything special here, so we're not going to do any of the optional models for this. So the physics have been selected. I'm going to go ahead and hit close. And I told it was a gas, and by default, it assumes any gas is just going to be air. I could tell it to use a different gas. I could say replace this air with something else, but I'm not going to. We can set some initial conditions down here. Under continue, under physics 1, we can tell it, hey, what's your pressure? Hey, what's your temperature? Etc., 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 yada, yada, yada. What's your initial velocity? Oh, one important one, reference values. Reference pressure. This is the pressure it assumes everything is at, or relative to, excuse me. Unless it says absolute pressure, every single pressure STAR-CCM reports, unless it uses the word absolute very specifically, is with respect to this pressure right here. By default, it is sea level. We can change this. We're not going to for the moment. But that is a static or a sea level pressure of 101,325 pascals. What else? Boundary conditions. Well, we're going to tell it that the outlet, the top, and the bottom of this are going to be pressure outlets, and the inlet is going to be a velocity inlet. So flow comes in the front, and flow is allowed to enter or leave through the tops and back of this as needed. And our velocity is going to be... That's a good question. What should it be? So if we're doing a Reynolds number of, let's say, 50,000. Let's actually say 40,000. So viscosity is approximately 2 times 10 to the negative fifth, and that's in the denominator. So right off the top, we're 2 times 10 to the 5 times 0.2, going to be 4 times 10 to the 4th, which is 40,000. Density is like 1.2 because we're talking sea level. So really 1 meter a second, I think, gets us, honestly, like a Reynolds number of 40,000 or so. But let me validate that by actually asking the calculator to verify this. So 1 times 0.2, that's our radius, or that's our diameter, excuse me. Times 1.225 divided by the viscosity of air at typical temperatures is 1.81 to the negative 5. Clearly I mucked... Oh, 0.2, not 0.5. I mucked up my math somewhere. So 1 meter per second gets us about 13.5 thousand. So we're going to start with 5 meters per second. This gets us a Reynolds number of... hold on, 6? I kind of want a nice round Reynolds number. 5.5. Okay, 5.5 gets us not quite, but pretty darn close to 75,000 Reynolds number. Now, one thing is, we don't have a mesh. We've defined our geometry, we've defined our boundary conditions, we've defined our physics, but we do not have a mesh yet. It hasn't broken down this region. So let's go ahead, and for starters, we're going to create a new mesh scene. And, well, it kind of looks like it has a mesh, but this is what's known as a, I'm blanking on the term in question. A surface or a geometry mesh. This is just how it's defined the geometry. Clearly, this is not going to be great for simulation because what if the pressure in this big triangle is the same everywhere? It's not going to be very accurate. Like, could you try and ask it to simulate this? Sure. Wouldn't work. So we need to go over here to operations, new mesh, automated mesh 2D. And we're going to mesh our subtract. Now we have a choice of meshes. This is basically what are the elements shaped like. When we break it into pieces, what are they shaped like? And again, there is a video. Here. There is a video. It's about an hour long, all about meshing. I recommend you go through and watch that. For this, I like, for 2D simulations, I like a polygonal mesher. And we will need a prism layer mesher. So polygonal, prism layer. The prism layer will deal with the boundary layer, and the polygonal will mean we just have polygons. So generally hexagons or pentagons. It can do higher or lower order polygons, but they will all be polygonal, rather than purely rectangles or purely triangles. So base size, I'm thinking 1 centimeter, but we'll see how well that goes. Minimum surface size, yeah, honestly, again, by all means, look at the meshing, the word I'm looking for. Look at the meshing video that I posted, because that will tell you what a lot of these values do. I don't want to particularly repeat myself on all of them. But we manipulate these values to choose how it breaks down the space. Let's see here. Theoretically, there we go. It created a mesh. It needs to be improved in, well, a lot of different ways, honestly. So we're going to use some custom controls to do this. Right off the top, the couple things are, we have really small cells out here where we don't need them. So I'm going to basically tell it, hey, on these 4 boundaries, do something different. That's the concept of what this control is doing. So the bottom inlet, outlet, top. I'm going to say, hey, the minimum is going to be a lot bigger, the target's going to be a lot bigger, and we want no prism layers. So if I tell this to execute right here, that already looks a lot more reasonable. I'm going to change the surface growth rate so these cells don't change size nearly as fast, because those are changing size really fast. This is already looking a lot more reasonable. Still not reasonable per se, but a lot more reasonable. This needs to be more like 75%, I think. That's better, I think. Now, if we want to tell this as cells can only get so big everywhere, we need to do this. Again, I refer to the meshing simulation because I'm just going through this pretty quickly. But we're probably going to set this up as, let's see here, a surface control. So this is going to be a max cell size. Did I not rename that? Rename. So this target is going to be 400 on that. Yeah, that's right. And then if we hit execute again, we should see that all these cells will get a lot smaller back here. And last but not least, we know this is going to do complicated stuff behind here. We probably want to limit its size a little bit. Actually, I'm going to turn this up to 800. But we're going to do what is known as a wake refinement behind the cylinder. So it's going to refine the wake of the cylinder. Let's see here. So this is a little option. We come down here, wake refinement, we check the box, and we get some values we can mess around with. I'm going to say for 4 meters behind the cylinder, it's going to make it a maximum of 25% of the base size. Cells can only grow so fast. It is going to be in the positive X direction. And we're going to give it a a 2-degree spread angle. And I'm also going to knock down the base size to 0.5 centimeters. I might regret this, but we're about... I'm probably going to regret this. So let me turn up this wake refinement size, and we'll see how long this takes. Oh, I'm also going... Oh, well, this is 2D, so never mind. Normally, I would set this from serial to parallel, but this is a 2D meshing operation, which only ever can use one thread, which means that I can't set it to anything other than serial or concurrent, and concurrent doesn't matter because we only have one part. Okay, let's see here. How many cells are we talking about? You notice it spits out a whole bunch of data over here in this in the console. Mostly that tells you, how much time is it taking, how long is it working on a thing, etc. So this mesh has about 450,000 cells, and yeah, that wake refinement is probably a little bit finer than it needs to be, honestly. I'm starting to think this base size is actually smaller than it needs to be. So we're going to double the base size and execute again, and it should mesh a lot faster now. Oh yeah, that was a lot faster. The other thing I'm going to do is probably one of the last things, is I'm going to turn down the surface growth rate some more. I previously had it at 5%, that is 1.05. I just turned it down to 1.02. And the idea here is that out here it won't do very much. But in here, it'll make these cells grow slower, so we get smaller cells closer to the cylinder, and we get a better idea of what does the pressure distribution around the cylinder look like. They still get pretty big out here, but in here they're a lot smaller. And we're down to 200,000 cells, which is much more reasonable. Probably still honestly more than we need for this, by a pretty fair margin, but more reasonable. So, now, in general, I recommend... Well, you know what? We'll go through. Well, let's set up some reports here. So I want to say, hey, what is the force on our cylinder? So, edit. So this is a force report. This measures force in newtons in our laboratory reference frame. This is going to look at force in the x direction. Conveniently, this is drag, so we don't need to change that. This needs to be force on our cylinder. And really, that's all we need. This is drag, and this will measure the drag on the cylinder. We're also going to measure a force coefficient, which is going to be the coefficient of drag on the cylinder. Now notice that this has some reference values. We do need to still tell it to look at the cylinder, but we also need to tell it, hey, what's the reference density? 1.18, I believe, because this is 300 Kelvin. It's 5.5 meters per second, and it is a 0.2 meters by 1 meter depth. So 0.2 meter diameter by 1 meter in the z direction. So the reference area is smaller than it assumed. If we did not change these, it would give us basically gibberish for our what's the word that I'm looking for? It would basically give us gibberish for our coefficient of drag. I'm also going to ask it for the maximum and minimum static pressure. New user minimum. The stat max and min. So I can select both of these and edit them at the same time, conveniently. So I'm telling it both of these are looking at static pressure. Both of these are looking at static pressure on the surface of the cylinder. And I'm going to actually do this co-located field function, which says, hey, what are some other values that occur at the same point that this maximum or minimum occurs at? I'm just going to ask it for the position in x, y, and z coordinates. That is where, conceptually, is the min and max. I'm going to hit save. I probably should have hit save a while ago, honestly. Stopping criteria. This tells the simulation when to stop. By default, the only one that's there is it says do 1,000 iterations and then stop. I'm going to turn that off because I don't want that to be there for now. And then I'm going to create a pair of scenes, or maybe more than a pair, but I'm going to create one for static pressure. I'm going to create another scene for velocity. So this is going to be a vector scene. I'm going to change it to line integral convolution. Again, this is not intended to be a explaining all of this. This is a brief, like, this is what the process looks like. There is a video on reports, monitors, plots, and scenes. It's a little bit more than an hour on the playlist I've linked. You should go look at that. So the vector scene, looking at velocity, that should be fine. Okay, so it's all grayed out because there is no values yet. We haven't started the simulation. We haven't initialized it. I'm going to hit initialize, and it's going to have values for this, but they're not simulated yet. So I think I can just hit run, and it should do things. We can see it start to figure out what's going on here. Oh, I created these reports. I did not create plots. So I'm going to say create monitor and plot from report. Create monitor and plot from report. And then create monitor and plot from report on a single plot. So to know if the simulation is done, really we want to see things stop changing. We can look at a vector scene and see, how stable does it look. Now the answer is ultimately these things will never quite stop changing, but they'll start to oscillate around a value, and the value they oscillated around will be constant at some point, or approximately constant. So we're just going to let this go for a little while and take a look at it. And it's a little bit annoying having the limits of this color bar change so much, so I'm going to tell it to stop changing the limits of that. Ditto on our static pressure scene, I'm going to have it stop auto ranging. So I'm just going to tell it don't auto range. Yeah, this might take a little while to actually work. Because you can see this oscillation, it's oscillating a lot, but also the value it's oscillating around is kind of changing. So we'll have to let this go for quite a while, honestly, to have a good idea if it's done or not. Pressure does appear to be more or less figuring out what's going on. Okay, it's hard to tell because this flow is extremely unsteady, but it looks like this is honestly getting pretty close to convergence. Like, again, is it oscillating a lot? Oh, abso-freaking-lutely. But the point it's oscillating around, it actually seems to be fairly constant. It's got this cyclic period of big oscillation, small oscillation. And the center of these oscillations appears to be pretty much constant. Like, this entire block isn't walking down or up, it's trending pretty much flat. I won't be really comfortable with this probably until it's run 3 or 4,000 iterations, but I'm confident enough that I think it's doing the right thing that I'll let it keep on going for a while longer. We can see what the velocities look like. We can see what our static pressures look like. We can see what our drag looks like. We can see what our coefficient of drag looks like. So we're looking at a value of probably about 1.15, 1.2, somewhere in there. I'm going to stop this temporarily, save, and run some more. And actually, let me see here. I think trigger normalization. I'm trying to remember how you do this. There's a way to do. So this is a little bit of an aside here. But there's a way to make it so that it takes basically a rolling average. I'm trying to remember how to do that. Let's take a look at the help documentation, which is probably a good thing to look at. So STAR-CCM plus. Let's see here. Coordinate system averaging. Da, 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 da. This is a the report. Oh, sliding, I think. There we go. Using a sliding sample window. Let's see here. Let's see here. So monitors, new, field min. Enable sliding sample window. We'll do 10. Oh, actually, hold on. What's the period here? Iteration. So period to period, we're talking about 100. Ugh. Yeah, we'll do a sliding a 100 sliding window. Then field max, static pressure on our cylinder. We want to look at a sliding window that is again 100 wide. I have to enable it. There we go. Enable that, and then can we... Interesting. Why does it not want to let me do this? Well, I forget how the hell this is supposed to work, but theoretically you can also do fields. Oh, maybe it's because it didn't have the number of samples it needed. No, that wasn't it. No matter. But in any case, yeah, this is, like, again, not steady state, but as steady as it gets for something like this. You can see the wake is pretty much just a straight line. We have this compound shedding happening. And we don't have to even look at redoing this entire thing if we want to change the Reynolds number. We can, and this is kind of going to be the last thing for today, we can just go to the inlet and we can say, hey, I want to look at a different velocity magnitude. I'm going to look at, instead of 5.5, I'm going to look at 22. I'm going to quadruple the velocity and hit run. It's going to take some time to figure out what's going on, and I need to let it redo the min and max values here. And it's going to take some more time to figure this out. We can see the coefficient of drag just jumped. But that's not actually necessarily because of anything we did other than change the velocity. So you reset the reference velocity to 22, we see that it actually drops down to not quite where it was, but in the same general neighborhood. And it is still working on this, mind you, so we can't, like, consider it done yet. You see all these residuals are moving around. Drag's moving around somewhat. Our min and max pressures are probably also moving around. Yep. But eventually these will converge again. These will become either, well, as constant as they get. And then we'll have new results for this higher velocity. And honestly, it's kind of already figured it out from looking at this. Like, this does not appear to be doing anything like drifting up or down. So it's probably already pretty close to converged, honestly. Maybe not quite, but real close. And you could even change the geometry without redoing the entire simulation. So I'm going to save this right here. But hypothetically, if we wanted to look at a relatively complex scenario, such as cylinders that were sort of not nested, tandem, one cylinder in front of the other. We're gonna make this like 0.6, I think. Create, and then we can just come down here to operations, and we can say, hey, instead of just subtracting one cylinder, subtract both of them. We can just tell it to redo all these operations. It'll remesh this, and there should be a hole that shows up right about here in this mesh. Once it finishes, of course. And on some levels, it didn't like that very much, but it did not crash, at least. And it's figuring out how this is supposed to work. And this flow field is going to get a lot more chaotic because it's a cylinder shedding flow into another cylinder. So this is going to do a lot of weird things. But you can change a lot of things without actually necessarily resetting the simulation. Sometimes you should reset it, but you don't necessarily need to. So this is not obviously the configuration you should be looking at, but the ones we looked at earlier, just a sphere, or a cylinder, excuse me, and seeing what does the flow around it look like. That's what assignment 1 is. And we're interested in the drag, we're interested in the max and min pressure coefficients, we're interested in the velocities, things like that. So I'm going to go ahead and stop this here and end the video. So that is sort of a very quick primer in the workflow for a basic simulation. Again, there are individual videos in the playlist that I linked for these different steps. There's a video on geometry, there's a video on selecting physics, there's a video on selecting or creating regions. There's a example video for a basic converging nozzle. How do we create meshing? How do we select boundary conditions? How do we create reports, monitors, plots, and scenes? How do we tell if it's converged or not? And then some other ones that we shouldn't actually need just yet. So I will post this video up to Canvas, and we will talk about this more. Well, I would say tomorrow, but technically today now. It's after midnight.